this is a very, very interesting project. And I think some of you who will, you know, in the future will be doing, taking 2799 or doing MQPs, they could think about taking this as an MQP project or a mini MQP project for 2799 and maybe can build upon it. Okay, so just to give you an idea, this is a solar tracker. Okay, does anyone know what solar tracker is? Has anyone heard of that before?
I think it's used for like solar panels, and it'll use the two photo cells or photoresistors to locate where the most intense light is so that it's getting maximum exposure to the sun.
Correct. That is absolutely right. So imagine you have the sun over here, okay? You have the sun over here, and it's emitting light, okay? Obviously, you know, sun is gonna be moving over a period of time. So it's maybe starting here, and then it will have a projection like this, okay? So if you have a panel, okay, which has the orientation something like this, okay? This is your panel over here. So right now it's getting pretty good light intensity. Remember, the more intensity it is, the more photoelectrons carriers will be generated, and that would mean it would emit more electricity. But when the sun goes over here, you know, then, you know, the way the orientation of the panel is such that a lot of emission will not get to the meat of the solar panel over here. So we would want it to, as the light intensity changes during the course of the day, we would want the panel to change its orientation, maybe go it like this, you know, something like this during the day. So it just, you know, changes its orientation, basically tilting it. Most of the panels that you have seen, you know, in Massachusetts, if you move around, there are a lot of solar fields. Those are fixed. They don't move around, okay? So a lot of energy is just being wasted. So in California, if you go, or I had the option, you know, one time I went to a conference in Colorado, almost all of the solar fields, like huge PV arrays, photovoltaic panels, they are fixed. They're not fixed, they have the solar tracker on them. So again, depending upon the light intensity, they change their orientation while they're fixed, but the panel can move around to make sure you get the maximum light intensity, which would mean maximum energy being created. Okay, so that is just the core of our today's lab. This is what exactly we are going to make. Okay, so now if you look at the circuit closely, okay, the heart of this circuit is basically the two comparators that we have over here. The two comparators, these are OPAMPs, okay? You have done OPAMP in the previous lab, so you know what exactly they are capable of. And we also, from the previous lab, we all know that you also have this LDRs here, two of them, one on each side. You can think of it, you know, those are being, you know, on each side of the solar tracker. And when the light intensity increases, because there's an inverse relationship between the light intensity and the resistance, when the light intensity increases, the resistance decreases, correct? So here LDR is connected in series with resistor right here. And then it is then connected to the non-inverting terminal, okay? This purple wire that you see over here, now I'm making it yellow. Maybe I can change the color to purple. This here is then connected to the non-inverting terminal, and similarly over here, non-inverting terminal. So what is happening here? When the light intensity increases, the resistance decreases. That means the voltage across this terminal and this terminal is going to increase. Okay, we got that part. Now the output of the voltage comparator, which is this right here, this here, and over here, this right here, pin number 6. When the output of the voltage comparator will be high, when the voltage at the non-inverting terminal, this terminal, this is the pin number 3 non-inverting terminal, is higher than the voltage at this terminal over here, which is the inverting terminal. Okay, and if you notice, this inverting terminal is connected to the output of this potentiometer. So you have the potentiometer connected to the pin number 2 of this op-amp, and also over here also. You're gonna make this potentiometer set to a fixed value, which will generate some voltage, and that would be a reference voltage for you. The sensitivity of the both LDRs can be adjusted by varying the this value, potentiometer. You can change the sensitivity of it if you like. When the light falls on the LDR, like this, the voltage at the non-inverting terminal of the corresponding comparator basically increases. And when that increases, the output of the op-amp goes high, okay? So that is what the op-amps are doing. They're basically working as a comparator, okay, where they are measuring the, or looking at the voltages which are dependent upon the light intensity. Another which is an important part of this circuit is this configuration right that you see in the middle. This is what we refer to as an H bridge, okay? And I'm going to show you what exactly they do, okay? These are usually transistors that we learned yesterday. The N that you see over here means it's in an NPN transistor. P would mean this is a PNP transistor. You know the difference between the PNP and NPN now. NPN electrons, they take part in the conduction. In the PNP, it's the holes, they take part in the conduction. Electrons have higher mobility, holes have slightly less mobility. Okay, now consider the case here when the output of the first comparator, let me just erase some of the stuff here. Okay, so we have the comparator number 1 here, and we have the comparator number 2 here. When the output of the first comparator is high and the output of the second comparator is low, so this is high and this is low, okay? The wires that you see in blue here, these blue and these blue, these are the output of the comparator, of the op-amp. And notice the output, these output wires in blue are then fed into the base of these transistors, okay? All right. So, and the output of the second comparator is low, and output of the first comparator is high. In this case, Q1 and Q4, which are basically these two, this transistor and this transistor, these will be on. And when they are on, the resulting current rotates the motor in a clockwise direction. This will move in a clockwise direction, okay? If I swap such that the comparator value, the output of the op-amp is low comparatively to that of this, then the motor, then these two transistor will be on, but in now the motor is going to move in the what do you call it, counterclockwise direction. And I'm going to show you the simulation also. So in this case, you know, like I said, these two transistor will be on, and the resultant current rotates the motor in a counterclockwise direction. If the output of the both comparators are low, means if both are low, this is low, this is low, what do you think what should happen? Remember, this is a comparator and it's comparing the two voltages, and based upon that, it is being fed into the input of the transistor where it draws the current. If the output is low for both the comparators amplifier, what would happen to the current that is being driven into the motor? Will there be any current? Yes, folks.
No current.
No current, because the transistor will be off, these will be off, these will be off, no current flowing through the motor. And similarly, if both the comparators are high, if both our comparators are high, you know, and because both are high, again, the difference will be zero, transistors will be off, and nothing will go into the motor, so they will just stay idle. Okay, so I'm just gonna give you a simulation here. This is the circuit that I shared with you on the condensed version of the lab 5. If I run the simulation and I have the a light dependent resistor on the left and also on the right, I'm going to increase the intensity. Notice the motor it started, you know, rotating in a clockwise direction. Okay, now notice the light dependent resistor on the right, I'm gonna change the intensity of that, make it both high. When I do that, notice there's no current being drawn through the transistor to the motor, and motor just stops. Okay, now let me change the light dependence, like intensity of the left LDR, make it 0. As I do that, now the motor is working, but it's not moving in a clockwise direction, but in a counterclockwise direction. Okay, so what I want you is to create this circuit, play around with it, change these values of this potentiometer as you see, and see how it is affecting the speed of the motor, direction of the motor, and you know, measure the voltages across at the input of the transistor and at the output, and see what exactly is going on. So just basically explore it. Before this, I have actually given you, you know, a theoretical aspect of every lab, where you would, you know, read about the theory and then you would make a circuit and then implement it. Today I thought of maybe just doing it like reverse engineering, in a way that I am giving you a circuit, you make that circuit, and look, you can obviously, you know, look at the functionality of it, but I just want you to explore it, change the intensity, what happens, change, hook your multimeters, maybe, you know, over here, you know, see when you change the resistance, what happens to the voltage, what goes in here. Similarly, when you change the light intensity here, how it affects the voltage over here, how it affects the voltage at the output. When you change the value of the potentiometer, how it affects the output. So just observe, change and tweak these parameters around, and just, you know, answer some of these questions. So I go search, I go to people, and I go to, just put my last name, that's me, circuits. So it is over here. I hope you can access to it. Can